YouTube live.
So now it's
Live stream. Okay. Okay. It needs 10 seconds or so. Then let me see. YouTube. Can you see?
Okay, let me check.
Yeah. I think I can see it. Yeah, I can see
it. It says going live already, but
okay. Yeah, I can see that.
Okay.
And again, Nabujiko, you'll keep an eye on the questions and stuff, right?
Oh, sure. Yeah.
Oh, I see. The YouTube, YouTube page and the link, they're separate links every time it goes live. So it makes a separate.
Okay. Okay. Let me see. And
so we just need to. I'll just give the web page.
Yeah. The web page. Yeah. You can go to the web page.
Yeah. Just give the YouTube page link. Yeah.
Okay.
Okay, that's it. Because yesterday
you have the YouTube. Okay.
Yeah, I just went back to the YouTube page, original YouTube page link, and there it shows like this is online live.
Okay. Okay.
I'll do that. Don't worry about it. It's okay.
Okay. Okay. Thanks. Okay. Let's get started. Hello, everybody. And this is BCVSPIN school, the online school day 2, and we begin with the second lecture on this second lecture by Professor Nashin Shah on standard model. Okay, so Nashin, take it away, please.
Hello, thank you for that. So I'm going to continue with talking about the standard model and the Higgs, but today I'm going to focus more on beyond the standard model, right? So the idea was that we need to understand what we see in the standard model. And again, I want to stress that what we have built up of the particle content over the past 100 years or so is a very empirical picture. We don't have a deep understanding of why we see what we see. Okay, that goes for the particle content, and that also goes for the interactions, etc. And when we're wanting to go beyond the standard model, that means we want to gain an understanding of what kind of bigger theory, hopefully, that exists that explains the phenomenon that we see in the standard model, right? I mean, so the goal is to go beyond the standard model to understand the big picture. So, I want to start off with, a reminder, the main picture that we have about the Higgs mechanism, which seems to underlie, a lot of the structure that we see, this idea of symmetry breaking that happens, which is what gives rise to all the fermion masses, the gauge boson masses, and also this weird, what I've mentioned before, this mixing that happens between the different fermions as well. So as this was asked in one of the questions, that the potential for the Higgs that we write down in the standard model. We don't actually know where it comes out. We just write down basically the simplest thing we can, okay? There's no deeper reasoning than that. The other thing I wanted to actually stress is when we talk about the Higgs as a vacuum expectation value, which then gives mass to the particles, it's kind of a weird thing in the sense that it's almost like it's taking away energy. So what you should think about the Higgs field is something more like, water, okay? So imagine that you shoot a cannonball underwater versus in air, right? So there's an effective resistance that this cannonball feels when it's transversing the medium, and you can denote that by an effective mass this cannonball has gained. And that's kind of actually what's happening here with all the fermions, gauge bosons when they interact with this background Higgs field. If there wasn't a Higgs field, these things would all be massless and they would be traveling at the speed of light. But they interact with this background Higgs field and they gain a mass, right? And like I said, the analogy that I would want you to have in your mind is something like, something traveling through water and getting an effective mass because of that. Anyways, so we spent a bunch of time going through that. Okay, so this is the simple picture of what we call the standard model like Higgs. And what we have observed at the LHC is in fact something which looks very much like a standard model like Higgs. And that's governed by, the vacuum expectation value that it has and how that relates to the masses that we go out and measure of the standard model particles. And then that if it's indeed the standard model like Higgs, there should basically be a proportionality factor between these two quantities, right? So we look at the coupling and we compare it to the mass and we see that they're proportional to each other. So now if you want to add additional states, additional scalars, doublets and singlets is what we briefly discussed, you have to be able to reproduce the same phenomenology, right? So what we had talked about is this phenomenon of alignment in which you get a standard model like Higgs, which does all of this stuff, even though there are additional doublets that could be there in your theory, okay? So that was the first thing we had kind of talked about. So continuing from there, the other thing that it needs to have is that this state that we've discovered has to have a specific mass. We've measured the mass of the standard model-like state, and it's right about 125 GeV. So how do we do that, and where did that come from? Well, again, this was asked last time, where does the mass of the Higgs comes from? And, again, writing down the standard model like Higgs potential, you can write down the vacuum expectation value of this, right? It's just you look at where that is. And this was the picture that I had shown you before, this Mexican hat potential, right? But the reality is that we have very little information about the full shape of this. The only thing we know about is this little part which I'm showing you up here, right? Only the location of the minimum, which is the value of this VEV, and the local curvature, because the mass is basically the second derivative of this potential at the minimum. That's the only thing you know, okay? So from this simple picture in the standard model, basically all you know is that somehow this parameter over here is a negative mass. Is a negative mass parameter, because the Higgs mass itself, that's the physical parameter, physical quantity, sorry, that is a positive thing. Okay, but the point is that if this thing was zero, okay, if the physical mass of this Higgs boson was zero, the Higgs part of the story, the Higgs potential, doesn't actually have any additional symmetries, okay? And what that translates to is that basically no symmetries actually protect the Higgs mass. And so any kind of quantum corrections, they make this unstable. And so you expect that they're going to be quadratic divergences, okay, when you include quantum effects. And in fact, you have the top quark. That's the heaviest particle in the standard model. And it basically has a coupling of 1 to the Higgs. All right. If you look at, this type of contribution of a top quark loop to the Higgs mass, basically bottom line, you get something, this lambda here is some sort of high energy cutoff. And if you assume that's somewhere, some high Singlet and Planck or something, you get, this contribution to this Higgs mass squared will be proportional to this cutoff. So, and similarly, if you had, additional scalars beyond the standard model, they can have different couplings to the same, HH thing, to this delta MH squared, and they would also have, this contribution proportional to whatever cutoff you have. And so the point is that you would need to have large cancellations, basically between different contributions, so that you produce actually a physical Higgs mass of 125 GeV. So then the question arises, are there some symmetries which govern the fact that there have to be these cancellations? But you have to keep in mind that maybe that's just the way it is, right? I mean, maybe it is fine-tuned, and or at least the next level up of understanding that we get, it'll still appear to be fine-tuned. But that's another thing that we look for when we're looking for additional extended Higgs scalars, Higgs sectors, what could be happening is maybe there's an explanation for why the Higgs mass is what it is. Apart from just the Higgs properties itself, though, when we're looking at the standard model, you also have to think about, in particular, the properties of all of the different interactions, et cetera, that we have observed over the past decades, okay? So these are, you can kind of put them together in what are called electroweak precision tests. There's a whole plethora of these different quantities that we have measured quite precisely over the years. And so this is things like, the mass of the different gauge bosons and their widths and stuff like that. And because the Higgs is so intimately connected to this whole idea of electroweak symmetry breaking, et cetera, the Higgs plays a role in a lot of these quantities. And so from measuring all of these quantities here, you, even before the discovery of the Higgs, you could try to figure out, well, where does the data point me to, like how heavy should the Higgs be? And even before the discovery of the Higgs, we knew that the Higgs had to be somewhere around 100 GeV or so. So that's great. But what happens if you have now additional Higgses? Well, the thing is that if you did have additional Higgses, they could also contribute to various electroweak precision observables. So the main way we do this is parameterize this in terms of these STU parameters. And I define what these things are here. Basically, new physics contributions, which differ between, at low energies between neutral and charged, so W and Z processes. You can look at the differences between the W and Z processes at different energy scales, and also in particular the W mass and width. So the left plot here, for example, looks at these ST parameters, and this is where you should live in these ellipses over here, according to all the data. And this line here is if you had a standard model like Higgs with some parameters, as you vary the Higgs mass, okay? So now we know, knowing the Higgs mass, we live somewhere here, but if you now change, what the different values of the different additional Higgses are, and some other parameters like the mixing angles, et cetera, this can change where you live, okay, where your BSM theory lives. Okay, so these additional Higgs bosons can contribute to these things, but you can still be consistent with all of this stuff. On the right plot is the similar things, like these are all these different parameters that are what is the best fit, where are you allowed to live in the masses, in the mass planes of these additional Higgses, and basically the colors show you where you're allowed to live for different, again, charged Higgs masses. And the bottom line is that whilst these additional Higgs bosons can have large contributions to these electroweak precision tests, if two of the mass states, the additional states, are approximately degenerate, then these constraints can be very minimized. But again, whenever you're building new stuff, you need to make sure that you take all of this stuff into account. Now, the next thing is the fermion couplings. So I've mentioned that, how would you be able to, if you were looking at the LHC, et cetera, how do you tell, what do you see? And that is going to depend on how things are produced and how they decay. And that is very dependent on the fermion couplings. So, and again, you have to be consistent, first of all, with the standard model. So the first thing is flavor changing neutral currents. So in the standard model, there are no flavor changing neutral currents at the tree level. This is governed by what's called the Higgs mechanism, but basically it's a statement that you can't have like a top quark convert to an up quark, all right? So this here is the Lagrangian, the standard model Lagrangian effectively, okay? So this is the Yukawa for the down type quarks, the up type quarks, and the leptons, okay? So these have different matrices over here, and they all couple to the Higgs over here. So now the thing is that in the standard model, this matrix here, the YD and the Y up, can be diagonalized independently. And that's why you don't have any flavor changing neutral currents. But if now you're going to some generic theory with additional Higgses, and additional couplings, then for example, you could have that, the same standard model quarks, okay, this Q left, D right, could couple to two different Higgses, H1 and H2, with two different matrices. And so the point is that generally, though, in this case, you can't actually diagonalize both this X1 and X2 at the same time. And so that would mean that one of these would cause these flavor changing neutral currents, one type of quark would change to another one, all right? And that's something that, again, you can't have. So how do you forbid that from happening? So one way is to say that, well, we're just going to suppress these tree level flavor changing neutral currents. So you assume that these additional matrices, these additional couplings, they're actually maybe, they have some particular relationships. So they have, leading order, they're proportional to each other. And then maybe, the additional factors are suppressed by the small standard model masses and mixing angles, etc. So this is called minimal flavor violation ansatz, MFV. So that's something that happens in a whole bunch of different models. But the other thing that we can do is, well, we're just going to forbid these tree level flavor changing neutral currents. So you assume that there's, only one of these two things, X1 or X2, is non-zero. And these give rise to what we call the different types of 2HDM, two Higgs doublet models. So what this translates to is that each Higgs, each type of fermion can only couple to a specific type of Higgs. So here I, list basically the four common ones: type 1, type 2, lepton specific, and flip. So what that means is that, so you have the up sector, the down sector, and the leptons. So, you see in here that all of the up sectors couple to only phi 2. The down and the lepton can couple both to phi 2, both to phi 1, phi 2, phi 1, or phi 1, phi 2, okay? And the way we can enforce this is by saying that, there's some sort of symmetry that exists, and we have the Z2 symmetry that's generally used, which basically means, phi has to go to minus phi. And, fermions, the associated fermions that only couple to that have a similar thing. And so that decides that this Higgs can only couple to these type of fermions, okay, because you've imposed this symmetry and, given these things, these charges. If this Z2 is completely unbroken, then the additional Higgses do not acquire a vacuum expectation value or couple to any of the fermions. And that's what's called an inert doublet. So you just have like this random Higgs doublet, which is hanging around, okay? But you can have what are called softly broken theories, in which basically the interactions all preserve the Z2 symmetry. So, your interactions are governed by this, but you can in fact have this Higgs acquire a vacuum expectation value, etc. And the bottom line is that depending on which type of model you're in, you can have very, very different phenomenology. So going back to this picture that I had shown you earlier about alignment, and that was in particular, saying that, okay, one of them is this up, H up, and the other one is H down. Well, this picture just generalizes to, just replace D by 1 and U by 2 in this table that I just had over here, right? So phi 2 and phi 1 in the different fermion couplings. And you would still have the same thing happening, that if you have a certain combination, which I call H standard, that would have completely standard model-like coupling, and then this other guy would have these other couplings, okay? And we know that the H125 should mostly look like this thing here, right? And the other state would be this one. And as I've shown you this picture before, what you see at the Higgs will depend, at the LHC will depend on what these couplings are to the fermion. So for example, the dominant mode of production of these Higgses is by gluon fusion, okay, at the LHC. So these lines over here denote fermions. And since the Higgs couples most strongly to the top quark, this process, so going from a pair of gluons via a top quark loop to produce a Higgs, that is one of the foremost production channels, right? So you can see that, and then there's the other ones as well. But regardless, the point being that what these fermion couplings are really will define the phenomenology that you would expect at the LHC, okay? And you have to know what you're looking for to be able to go looking for it, right? At colliders, etc. So what does that actually mean? Like, what actually are these couplings then for these additional states? So I want to spend a couple minutes going through that. So as an example, let's look at the type 2 models, okay? And we'll start off with what I call the interaction basis. This is where the Z2 symmetry is defined, where you have defined that this H-up and decouples to the up-type fermions, the down-type fermions. And I've also included, a singlet here, which, because it's a standard model like singlet, it only couples to the Higgs, the Higgs sector, right? It doesn't couple to any of the fermions. And you have tangent beta, which is the ratio of the VEVs of these two Higgses that exist. And the singlet, I allow this to also be able to get in some arbitrary VEV. So it can have a vacuum expectation value, which is not part of the standard model vacuum expectation value, by the way. So when you have this, then you would get what I call the extended Higgs basis. So you will still have these states, which I call the H standard and H non-standard, which I showed you before. And you would also have the singlet. So if you look at their couplings, by definition or by construction, this H standard state coupling to the different fermions and what I call V is the W and Z gauge bosons, this will all be standard model values, okay? But if you look at what happens to the non-standard guy, what you'll see is that you'll get either tangent beta enhanced coupling to the down quarks or tangent beta suppressed couplings, so divided by tangent beta for the up-type coupling. And very importantly, this state does not couple to the gauge bosons, to W's or Z's, all right? So only this one couples, the H standard couples to the gauge bosons. The singlet, because it's a singlet, again, doesn't couple to anything. So now what we, however, observe is actually the mass basis, right? And that is going to be some admixture of these three states that we wrote down. So this is, what our mass eigenstates are going to look like. They're going to have some component of the non-standard, some component of the singlet, and some component of the standard model. And what we know is that we need to live in some regime of parameters where, you have one state at least, which looks very standard model-like, and that's the one which we would think about as H125, the state that we've observed at the LHC. But you have these additional states, okay, this capital H and this little h that I have here, which would be admixtures of this non-standard and singlet mostly states. Now I've also mentioned before that these are complex scalars, and so they have the CP odd part scalars that will come with it. And those, if you're assuming CP conservation, then they don't mix with these things here, but they can mix within themselves. And so they would also mix together to give you, two states which are CP odd. All right. So how does that now work like for the mixing angles? So given, let's say again, just the two states that you have, going from the Z2 basis, again, where we've defined the fermion couplings, to the mass basis, you would have some arbitrary rotation angle alpha, okay? What I defined as the Higgs basis is where you have one which is the standard model-like guy and the other non-standard. That is a rotation by an angle beta, which is the ratio of the VEVs, right? So we know this one well. And then, however, we always want to go to the mass basis, and it turns out that that can be written down as beta minus alpha. It's always going to be given by the difference between these two. But that is the quantity actually which we have information about. That's what we call, if this, so it has to be equal to basically pi minus epsilon. If epsilon was 0, it would be perfect alignment. And we know that we have to be living quite close to that experimentally. And so, allowing there to be this small epsilon, or allowing this beta minus alpha, right, to not be equal to so it's allowing this beta minus alpha, then you can write down for all the different 2HDMs, right, the different types that I showed you before in here, where you have the different fermion couplings. You can write down how the little h, the capital H, and the capital A, which is the CP odd guy, how they couple to the different fermions, right, that I denoted over here. Okay, so what does that get you? Well, first thing is, is that so depending on the different type of model that you live in, you are going to have different amounts of misalignment. So what we know is this cosine beta minus alpha has to be small, right? This is the amount of misalignment. And the sine beta minus alpha has to be approximately 1. Okay, this is just a translation of this statement over here. Okay, and now you can go and look at all of our Higgs precision tests. You remember this table that I had shown you of the Higgs couplings to various different things, and that it looked very close to what you would expect from the standard model. But there's error bands and et cetera, and you can look at, okay, where do I live in this plane of tangent beta versus cosine beta minus alpha for the different types of models. And the blue regions denoted in these different curves are the allowed regions that you can live in for the different types of 2 Higgs doublet models. So you can see that depending on which type of doublet you're living in, you can have large regions of a space which are allowed, and others where you're very constrained to be very close to alignment, right? I mean, alignment would be cosine beta minus alpha equal to 0, right? And it does depend on the tangent beta, which is again the ratio of the webs. Okay, so now, this is the Higgs precision stuff, which tells us about this misalignment story, but that feeds into how we look directly for these additional Higgses, okay? So again, how are they produced? How do they decay? So that's going to depend on the mass spectrum, like the masses of these additional states, what type of model, these are the different types, 1, 2, 3, 4, how much misalignment you have, this beta minus alpha, as well as tangent beta, right? This is the stuff that I showed you before. So using that, so these are, for example, assuming degenerate mass spectrum in the mass versus tangent beta plane for these additional Higgses. If you assume a type 1 or a type 2 model, these are various searches at the LHC. So, A going to HZ, or H going to WW, etc., and or H going to tau tau. The regions which are colored means that those are excluded, right? So again, depending on what type of model you have, there are large regions which may or may not be explored already, that we've probed already, and the regions we're still allowed to live in. Yeah. Okay. So what next? Well, apart from just this, very straightforward, okay, what are the fermion couplings and how do we look for these additional Higgses? The other thing that is super relevant is what are called flavor observables. We have various precision tests that we've been running, again, for decades in various processes. So I give a listing over here: beta S gamma, BS to mu mu, blah, blah, blah. So basically, for example, this is beta S gamma. Okay, so you have a B quark, and it has some loop here which converts to an S and also emits a gamma at the same time. And if you have these additional charged Higgs, those can contribute to these processes. Okay, so what this translates to is that you have very stringent constraints on the mass of these charged Higgses and on tangent beta. Now, there is a caveat to that, which is to these kind of constraints that you would get from these flavor observables, which is that, this is only considering the Higgs sector, okay? Just the particle contents which you get from these additional doublets. But if you have really a UV completion of a theory, you would expect that there are additional particles in the theory apart from just the Higgses, right? They could be additional scalars, additional fermions, et cetera, and they could also contribute to these kind of processes. And so in principle, you can have various cancellations that can happen that, even though, I show here, for example, limits on the mass of this charged Higgs versus tangent beta for, again, the different types of 2 Higgs doublets. And you see, okay, in this particular one, there's B2S gamma, really rules out everything below 600 GeV for the charged Higgs mass. But maybe there are additional particles in there in your theory, which would actually cancel this contribution. And so in that particular model, you would be allowed to live in it. So you do, with these flavor observables, et cetera, you have to think about your full model, and also, think about that if you are using this as a simplified model, the caveats that go into how stringently you take these constraints, right? How much weight you should put that really everything is ruled out or not. Okay. But again, a relevant constraint, you have to be aware that this happens and take that into account. So again, so putting that all together, you can put all of these different things that I've put it together, and that's what you would do, right? I mean, if you were looking at an additional extended Higgses that are coming in, you need to put in all of the different constraints that are there. You have to get a standard model like Higgs. It has to have the right mass. It can't mess up basic standard model predictions, and fit all of the different observations, etc. And that's the only way which then is the next step, which is like, okay, what new things can you learn about that? There's one last thing though that I didn't mention yet, which was CP. So CP is charge in parity, and the statement is that if you basically flip your charge of your particle, you basically go from particle to antiparticle and also parity, which is x to minus x. Then while the strong and the electromagnetic interaction respects that, it turns out the weak interaction does not. And in fact, this CP violation is super relevant for what I had mentioned yesterday about baryogenesis. Not only do you need to have a certain type of phase transition, there needs to be CP violation for there to be a matter-antimatter asymmetry that's generated. Okay, and we do know that in the standard model, there's not enough CP violation, but the Higgs potential, additional Higgses, could be a source of this. So, you have this capital H and this capital A, which is the CP even and CP odd guys. Because this is a complex doublet that we're talking about, so it has a real and complex part. So both are in the, so again, these can induce CP violation. And the properties, like which one is the CP odd and CP even, is defined by how they actually couple to the fermions. And the thing is that because of that, because of the fact that these things coupled into fermions, there are actually strong constraints which come from the EDMs, the dipole moments. So for example, we have, constraints of, these are some recent constraints on these things for the electron and the neutron EDMs, because, you can have this kind of contribution to these EDMs. So again, this then provides a very strong constraint on the amount of CP violation that you can have from these Higgs sectors. Okay, so where do we go from this? And you need to absolutely have empirical agreement with the standard model. And we don't actually have any kind of deep answer so far to the puzzle of basically the standard model fermion masses and the mixing. So the way I think about it is, we're trying to piece together different parts of the puzzle, and we don't necessarily see the big picture, but we can think about if we can, kind of put together little pictures together that can give us the ingredients of the actual UV theory that we're trying to understand. And so the way we do that is we build these models, and the parameters there basically are parameterizing our ignorance, right? We're putting them there because we don't know where they come from. But the hope is that, you know, trying to understand how the interplay goes in will give us insight into where they could have possibly come from. So the simplest story now that you could write down, so I want to go into a little bit more detail, is if you took if you took the standard model and you just added a singlet, in fact, a complex singlet. Okay, so here I write down, you know, the potential for this, for that you would write down just off the bat, just all of the different things that you can think of, the interactions that you can think of between the Higgs and a complex scalar. Okay, so the capital H here is your standard model thing, and this script S is a complex singlet, which has these two components, right? The scalar and the CP even and CP odd guy. And here, part of it is the standard model potential, right? That's still there. And all of these additional terms are all the possible ones that you could write down for the singlet. And then you also have things which mix together the H and S the terms, right? So this would give you the interactions between the Higgs and this additional singlet. So this is now, because this is a complex singlet, this is equivalent to having two real fields. And already you see that this looks much more complicated and nasty than this pretty little thing looked like in the standard model, right? So even with the simplest story addition, things get pretty complicated. So how do you go about, you know, trying to analyze this? Well, you hope that you can put in some sort of constraints, some sort of asymmetries, et cetera, and try to get, you know, you want to simplify the model so that you can understand it, but at the same time, try to do it in a way such that qualitatively you see the different features that you can have, okay? So you can, for example, put in a Z2 symmetry for S. So that eliminates, for example, all of the odd powers, and you could have a U1 symmetry, so none of these things, the coefficients can't be complex. You know, you could have, depending on if these things have mass, they could possibly be dark matter candidates. I won't talk about domain walls, but you know, this is also a possibility to have this electroweak phase transition, which goes to baryogenesis. So once you basically put these constraints in, you can simplify this potential to something which looks a lot more tractable, right? And then you can look at different types of cases that I was just mentioning. So you could say, well, you know, I'm going to look at the case where the singlet doesn't get a VEV, or it does get some VEV, maybe it has an additional U1 symmetry, maybe some of these things have masses, some not. Are they some stable, long-lived particles, which could be dark matter or not? And you put, you make the different qualitative cases, which hopefully will give you an understanding of how adding a singlet will change your story, okay? So you do that, and then, you would have to make sure that your potential, your electroweak minimum, when you minimize it, is actually a global minimum, so you don't have to worry about it being unstable, right? Because if it's not, then there's a possibility that the standard model vacuum is not the ultimate vacuum, and that you could have tunneling to another vacuum, which would be kind of catastrophic, or could be catastrophic. And then you minimize the potential and you diagonalize your mass matrix, so you actually then end up getting the physical masses and the couplings, which are related to the mixings of these different states. So I'm not going to go through the formulas here, but I've put them down here, and I hope that you can go through and look at them and work them out if you're interested, as well as the references. But basically, like I said, you minimize. This is simple, that you can minimize the potential by taking the derivative of this with respect to the different fields in here. So that gives you the vacuum expectation value for each one of these. And then you can take the second derivative of them to write down your scalar mass matrix. So in this particular case, this is what it looks like. Okay, so this is in the H standard X and Y basis. So these, X and Y are the CP even and CP odd parts of the singlet. And then you diagonalize this. So when you diagonalize this is, okay. And then you have to have that there's alignment, right? Because again, we know that the standard model-like guy should be pretty standard model-like looking, right? The H125, sorry, should be pretty standard model-like looking. So it can't have very large mixing with the other states. So you do that, and then you write down, your physical masses by diagonalizing this story, okay? So the bottom line, though, in this particular story is that you get basically a universal reduction of your H125 couplings to all of the standard model particles, which will be proportional to this parameter delta over here. And you could also have possible decays of your H125 into these additional scalars if these are light enough. But also, these could be invisible because one of these things in this particular case could be stable dark matter candidate. So anyway, that was like the simplest story that you could do. The next thing is, instead of a singlet, now this is a little bit more complicated, but you could, think about what happens when you add a doublet to your story. So this is what happens in a lot of things like SUSIE, and this was the whole thing that we were talking about generically in 2HDM. And again, the point is that we are using this to parameterize our ignorance, okay? So you start off writing down the 2HDM in the fermion coupling basis, the Z2 basis, where you define that, phi1 couples to this type of fermions, phi2 couples to this type of fermions. And again, the same parameterization that we've looked at before. You have tangent beta, one of them gets VEV, V1, V2, etc. And now here, you also will have for each one of them standard model potential like terms, right? And then you'll have all of the possible different mixing terms between all of these different Higgses. Here, you also have the possibility of CP violation. If you had these certain couplings here be complex. But for the time being, just assume that it's a CP conservation, okay, so CPC. So you assume that they're all real. Okay, and then you also want to have no flavor changing neutral currents again, so that also says some of these couplings should not exist. You have your alpha mixing angle, and you have to have alignment, right? So again, this statement, the cosine beta minus alpha has to be much, much less than 1. Sine beta minus alpha is equal to 1. So now certain things about once you write down the mass matrix for this. Again, you minimize it and minimize the potential, and you write down the second derivative mass matrix. The mass of the H125, so that tells you what one of the parameters is already. And this guy is basically your mass of the heavy Higgs. And that this thing over here is what controls this mixing. So you can parameterize these things in terms of like physical observable quantities, which is again the masses of these things, misalignment, etc. So this is, and then you also know what we talked about from electroweak precision and flavor, that you want either these A or H to be degenerate with these charged Higgs masses. So that constrains significantly the parameter space that you have. And in particular, once like I said, you have to put in the Higgs mass, and then you have to put in that it has to be alignment, right? So it tells you, certain things have to be either really small or certain things can be really big, right? The additional Higgs can be super heavy. And so that tells you that this mixing angle must be small and it is governed by these different parameters here, okay? And so, like I said, yes, it's governed by the empirical observations of your standard model like H125. So now we know that we live close to this line when we've been talking about this. But one of the questions is when you're now thinking about, okay, this is sort of a simplified model that we've been thinking about, but how do you actually, and of course you can impose that in a simplified model, but we want to hopefully get some deeper understanding of why things would be that way, right? And so we want to think about why, what are possible ways that you could actually get something like exact alignment. Okay, so the Z6 equal to 0. And there actually are 4 possibilities. So you have something which has, it may be an exact symmetry of the theory. Okay, so including the Z-to symmetry. So this means that the additional Higgs would be completely inert. So it doesn't actually interact with the Standard Model fermions, etc. at all. All right, that's why we call it the inert Higgs doublet. You could imagine that it's a symmetry of the scalar potential, but it's not respected by the Higgs-Yukawa interactions. But that again would mean this is generally not respected by the Yukawa interaction, so it would get broken there. You can imagine that it's some sort of accidental global symmetry of the scalar potential, which may or may not be broken by the gauge and the Higgs fermion interactions. The problem is that in this case, even if you did have this happening, most of the time this gets destroyed by loop effects. So it's really hard to actually have these symmetries work because you have quantum effects. But at the end of the day, I mean, maybe all you have, the understanding so far could be that there's, some reason it's an accidental choice of the scalar potential parameters, which is not governed by symmetry. And so far, it kind of looks like that, at least in the models that we can think of. Okay, so this is what would happen in your generic 2HDM. We just say, oh, the Z6 is just super small. But also in SUSIE theories, which is like the MSSM or the NMSSM that you would have, things just seem to work out like that. Okay, so we at this point don't have really any super great ideas about why the UV theory would want alignment to be happening. So I will mention, hopefully I should have time to talk a little bit about a case in the NMSSM where this happens, this seems to happen pretty beautifully actually. And it hints that there is some sort of structure which may be dictating this. But anyways, so what low energy insights do you actually get from alignment? That's the question, right? Especially when you're talking about, the Higgs pheno, what are you going to observe, etc. So one of the big things is that this really dictates the kinds of couplings or decays which are going to be suppressed because of the fact that you have to live near alignment. So for example, all of these that I list over here. So capital H, so the capital H and capital A, again, are the additional Higgses, right? They're coupling their decay, for example, into a pair of H125s or Zs or Ws, or a capital A into a Z and an H125. These are all suppressed, okay? And that's very simply because if you look at, this coupling, capital H to little h, right? And these are all related to precisely this vertex. If you rev one of these, then that is precisely what gives the mixing term between capital H and little h, okay? So that is why you have this intrinsic relationship between alignment, which is saying this mixing needs to be small, and the fact that these decays have to be suppressed, okay? And so, the direct searches at the LHC in these particular channels are actually complementary probes of the H125 Standard Model-like nature, right? This whole misalignment idea, this cosine beta minus alpha. Anyways, so the last thing I want to talk about very quickly is, to do with the 2HDMs, and hopefully I'll have a few minutes to talk about SUSIE at the end, is if you added now both 2HDMs and a singlet. So as you can imagine, things can get very, very complicated very, very quickly. And you have this huge, nasty mess with lots of different parameters. And you have now additional Higgses too, because you have the singlet scalars and the pseudoscalars as well. But you can still make progress by looking at, things that you can know, and what certain things have to be small, and certain things have to be degenerate from electroweak precision things, etc. And then you can consider also that that there's, like I said, that there's various decays, etc., that are suppressed due to this alignment. But now, because you have these additional singlets also there, they can be extra cascade decays, this H standard H non-standard decaying to a singlet plus H125, etc., which were not present otherwise. And that can give you an additional handle on trying to study these kind of complicated models. And you can also have, that these additional things may or may not decay invisibly. And so, this is sort of, so the picture is not hopeless, is my point here, that even with a complication such as this, if you actually put together all of the different types of searches, we look at all the different channels, then, I'm showing different planes and mixing angles and the masses, that if you actually include all of them, the colored part is things that we would actually be able to probe the parameter region if we included all of the different types of searches that we're doing, and also give insight on various different signatures that maybe we should be looking at, right, in the future, that maybe this type of signal could be hidden into. So I'm not really going to go into CP violation right now in the interest of time, but again, I'll have my notes up so you can look at them. But the point is, you can add the CP violation to this 2HDM that I just talked about. And now all of the states are going to be mixed and not have definite CP eigenstate. And the way you figure out what's going on is basically would be via either angular distribution of decay products, or you would look at various decays that you can have simultaneously, or something like H3 going to H2, H1, which would only happen in the case of CP violation. As I mentioned before, the stringent constraint on whenever you have CP violation would come from electron EDMs, but you can have cancellations also in these type of contributions, and may allow you to live in certain regions of parameter space. And you can have certain signatures. For example, you can have this heavy guy decaying into 3 H125 states with large amounts of data that maybe we'll be able to see at the LHC in the future. Okay, so in the last 10 minutes, I want to very quickly talk about how the Higgs sector works in supersymmetry. So, clearly that's not even close to the amount of time to do justice to this, but hopefully I'll give you, sort of a broad overview. So what's SUSIE? Well, really, I've mentioned it multiple times before, and I'm sure you've heard about it before, but there's a whole bunch of really compelling arguments for SUSIE. So there's this, has this understanding of the hierarchy between the different scales. It actually generates electroweak symmetry breaking dynamically. You have unification of couplings. It also provides, a good dark matter candidate. So we usually start off with what's called a minimal SUSIE MSSM. And that's just saying that everything in the standard model has a superpartner. Okay. And now, technically, if SUSIE was preserved, then each one of the SUSIE particles, the superpartners, would have to have the same, the masses as well as the couplings. Okay. But we know observationally that can't be true. We know that SUSIE has to be broken. Okay. So we, so we know that, these SUSIE partners have to have different masses, but they still have the same couplings as the standard model particles. Okay. So as far as the Higgs mass is concerned, the Higgs part of the story is concerned, you have a type 2HDM, and you have the generic form of the Higgs potential here. But now the thing is that because it's SUSIE, so there's, not everything is free anymore. And you have all kinds of different relationships between the different couplings that are there. And so these quartics, et cetera, that we had in all the different potentials that I'd written before, which were just arbitrary parameters, parameters that we really didn't know much about. Now these things are basically related only to the standard model couplings. So we can write down what that is, right? So all these type of interactions. And it turns out that the mass of the Higgs in SUSIE, in NMSSM, is bounded by mz at tree level, okay? So we know the mass of the Z, And well, it turns out it's 91 GeV. And that's, well, obviously not equal to 125 GeVs. So we need something else, right? We need probably, maybe large radiative corrections, which perturb that value from the tree level value. So I'd shown this before, that that whenever you have additional scalars, then you can have these large contributions to your Higgs mass parameter. And now the thing is that when you have SUSIE, so the top quark is the standard model particle, which has the biggest coupling to the Higgs, but you also will have the stop, right, which is a complex scalar, which is a super partner, and it'll also have exactly the same coupling to the Higgs. And so this guy is going to be there. And the interesting thing is now there's a symmetry which governs that there will be this cancellation between the top and the stop contributions. So the large quadratic divergences actually all cancel out. And actually these things then can, but you have these log contributions which are left over, and these can actually lift up the tree level Higgs mass from 91 GeV to 125 GeV. So I'm basically here writing down all of the different, contributions that you have for the different quarks in there, and then the mass matrix for the stops, etc. The bottom line, this is what the Higgs mass will be once you include these stop and top quarter contributions. So you have the tree level part, which is at most MZ, and then you have this additional stuff over here, which depends on the parameters of the masses and the mixings of these stops. Okay, so you can plot this out to look at what kind of stop masses do you need. And it turns out that, the stops need to be order of, so if you look at 125 GeV and the masses of these things, the stops have to be order a TeV or so with significant mixing to be able to reproduce the Higgs mass. And, maybe that's the case, maybe that's not. I mean, we're basically now starting to explore the region at the LHC, which would be dictated by looking at, the Higgs mass. Now, in addition to that, either you could, the situation with the Higgs mass could be these large radiative corrections, or you could have something else, right? And so the something else possibly is given by by what's called the NMSSM, which is basically the MSSM that we had before, but now you just add another singlet superfield. So now you get this, for the Higgs sector, basically you're getting the 2HDM plus singlet, but you also get the super partners of this guy, which is a singlino, etc. But the point being, this is still SUSIE, so you still only have a few parameters, this lambda, which governs the coupling of the singlet to the Higgses, this kappa, which is self-coupling, and a couple of other parameters, all right? So now here is something that really amazing happens, which is that if you have alignment, no mixing, and this value of lambda between 0.65 and 0.7. Remember, this lambda is the coupling of the singlet to the Higgses. The singlet contribution actually very nicely gives this additional contribution to this Higgs mass. Okay, so this is the MZ part, this is the lambda squared, the singlet additional part, and this is possible stop contributions again. So you very easily get the right Higgs mass of 125 GeV without necessarily large contributions from the stop sector. But what's not been appreciated previously is that for the same value of the Higgs mass, you actually, for the same value of lambda, et cetera, for Higgs mass, you actually get very nice alignment with the other Higgs doublet. So this is, for example, the coupling of this MSSM, the NMSSM Higgs compared to the standard model in the tangent beta MA plane. And these numbers here, so this is, a few percent deviation in the couplings that you would see. Okay, so it really does that really nicely. We don't know why that could be, but there's some ideas about, this could originate dynamically from Higgs compositeness at the gut scale. So the other thing is to note here is that you also have to, however, that was the doublet alignment. That works beautifully. But you also have the singlet in here, right? And you also need to make sure that you don't have too much mixing with that. And so you can write down what is the mixing with the singlet. And, you get your very simple equation over here, which depends on the masses, et cetera, and the parameters of this model. And you translate that to, for the mass planes. And the bottom line is, and I plot some of the relevant, the Higgs masses as well as the Higgs Xeno, which is the partner of the Higgs here. And the relevant part is that everything seems to be perfectly consistent for, order a few hundred GeV particles for everything. So in this very nice story, the H125, so the Higgs mass and its standard model-like nature in this SUSIE story looks like it would be very consistent with a light spectrum. And in addition, would have these additional singlinos, right? These fermions, which could possibly be dark matter. Okay, so you have this whole very nice picture. And then so this is, however, so far what I've showed you is very simple equations that we write down from tree-level equations of this NMSSM story. And you could ask, well, previously I've also shown you that, loop corrections screw up things completely, right? So should I really trust this? Well, the nice thing is that we have these very sophisticated tools, which include in particular for SUSIE models, which include a whole bunch of these different contributions that could be coming in there. And we could do these gigantic scans in this region of parameters, which include, like I said, all of these loop corrections. And we did that. And, basically you can look at, so again, this is a multidimensional parameter space with all the different masses, et cetera. But the point is that you can look at for these particular these mass correlations that are there, right? This is what I was just saying, that everything looks to be pretty light, and this actually seems to hold very well, even when you include all of the different loop contributions, etc. So again, it seems to me that this is the type of story. I mean, so again, the masses and these parameters that we've put in there is parameterizing our ignorance, right? I mean, we don't know where they came from. It's just, we put them there because there should be something. I don't know where it came from. There's some SUSIE breaking mechanism that happens, which should be part of a bigger story, which governs that, right? And that's what we're trying to understand. But we only have access to what's happening at the low scale. And now we're looking at the low scale, and there seem to be these really interesting correlations, which seem to tie things together. And so that hints to me that maybe that is putting together the picture of what could be happening at the high scale. So with that, I will end the story, and I hope you all enjoyed that and have fun in the rest of the school. Thank you.
All right, thank you very much, Nassim. A wonderful lecture. Okay, so now, all right, Q&A session, and I have, okay, let me check the chat window, and I have several questions. Okay, let me read one by one. Okay, let's see. The first question from Daga. Do neutrinos interact with Higgs field? How do neutrinos acquire mass? That's the first question.
So this is an open question, right? We don't know. So technically, you can write down the neutrino mass term just like you do for all of the different fermions, right? With a right-handed neutrino, you write down, it has a super tiny Yukawa, but we don't have any understanding of where the Yukawas come from anyway. So nothing's stopping us from doing it, right? And that coupling is so tiny that we have zero evidence, like we really can't directly go and look for a Higgs decaying to neutrinos at this point, yeah? But we don't know for sure, because the right-handed neutrinos are standard model singlets. They're not charged under the standard model symmetries. And so in fact can have just an arbitrary independent mass term, okay? That would, so they could have a Majorana mass term. And there are various theories with seesaw mechanisms and things like that. And, some of them, they would give rise to, for example, lepton number violation and things like that. And that is an ongoing question, because we do want to understand how that works, but we don't.
Okay. The next one from Himal. I think, all right, so does Higgs mechanism give particle mass? If yes, how?
Yes, because that was the starting point of today's lecture, but I spent also some time yesterday. So the Higgs field, acquires a vacuum expectation value. So everything that couples to the Higgs then acquires the that mass. But okay, maybe let's go to the Yukawas here. So here is the Yukawa interaction. Okay, so you have, this is some coupling here, this Y. So let's say this is for the down quarks. Okay, so the left and right down quarks, and this is the Higgs field. Now, if this Higgs field, this is the coupling between them, but this gets a VEV, so that would just be a V times the Yukawa, that would be a mass term. Okay, so the Higgs gets a VEV, and then these things get a mass. I hope that explained it.
All right. Okay, so let's go to next one. And okay, from Tom, can you explain the exponential term in the potential B in adding another complex scalar? Slide. I think this is a question for your discussion around page 30. Yeah, around 30 or 28, 28, 29, if I remember it correctly.
Oh, these exponentials.
Oh, yeah, that part. Yeah.
That's just to add possible phases that you can have. I mean, those are just free parameters. I mean, it's a way of writing a complex thing there, right? So R e to the I theta is the same as A plus IB. So it's just a way of writing a complex parameter, just, the magnitude times a phase. Some people like to do that. Some people like to use the same thing.
Yeah, okay. All right, so next one is from Dargo again. And do dark matter acquire also, acquire mass due to interaction with the Higgs field, or other mechanism, other mechanics are responsible for mass of dark matter?
We don't know. Again, mostly we have the most popular stuff that it doesn't have to have mass acquired by the Higgs. There's usually other things that are going on. But I don't see why it necessarily forbids it. Depends on what kind of particle you have and things like that.
Okay, all right. Okay, so next one. Okay, Sajib, can Higgs directly couple to the photons? Also, do they, Higgs, follow self-interactions?
Yes, so the Higgs does not couple directly to photons because it's not a charged particle, right? So, but at the same time, you will have Higgs to gamma-gamma coupling. And in fact, that's one of the search channels, right? And that happens because of loops. So so again, this is a tiny diagram, but I think I had it other ways placed too. But here, this is showing gluon with a top quark to an H. You would have the same thing for the photons here, with also W's in the loop. So you'd have like W's in there, and the different, again, the top would be the dominant contribution, but absolutely H would couple to gamma-gamma, but not directly, not at tree level, but via these loop process. And it, in fact, it's quite important. The Higgses do have self-interactions. So if you look at the Higgs potential and you expand it out, right, around this, let's see, if you take this this potential over here, or maybe I should show this one. Well, it doesn't really matter. And now you put phi in each one of these H. You put H plus V. You'll get all the trilinear, etc. interactions in there. And that is something that we are trying to understand and look for, because again, we only actually know this little part of the story. And, but these additional interactions that you may have could tell you about other stuff that's happening over there, because imagine that this is not a simple form as this, and you have additional terms in there, right? Then the self interactions of the Higgses that you could have could be different from what is dictated by just this. So that is an open question, and we're trying to nail that down.
Okay, so next one, Lomson, can we use the results from Wilson coefficient, standard model effective field theory, or anomaly cancellation to put some constraints on a BSM model's parameters?
I mean, yes, but SMEFT is, the whole point is like you want to parameterize, again, your ignorance of what's happening at the high scale. That's basically the idea there, right? That I don't know what's happening, but I can integrate it out, and this is the type of effects that I should have. And then you go and look, and there's a lot of work on that, different types of operators that you would produce. And, then you go and look at, okay, this, if you had this type of operator, which tells you an interaction, right? Then you go and look at different observables, which would get impacted by those interactions. And, you constrain those. Exactly.
Okay, then last question from George. Okay, the comments in there. Thank you for this interesting and informative talk. And I would like to ask you two questions. In slide 15, I think, you mentioned that the scalar S field couples only to the Higgs. Why is that the case?
It's a singlet, right? It does not have any standard model gauge charges. It does not have any of the standard model charges, which means that you can't write down an interaction with any of the standard model particles. Like there isn't any interaction that you can think of. So it can't couple to any of the gauge bosons, right? Because you have to be charged under that to be able to interact with a gauge boson, right? Only the electron, something which is charged, will interact with a photon. If you're neutral, you don't interact with it, yeah? And then fermions, because of this left-right business, there's no gauge invariant way, nothing that you can write down which respects the symmetries.
Yeah. Yeah. So actually, the question continues. You already answered. Does this scenario consider no fermion couplings to S, and the S couplings to Higgs can give us answer to why the Higgs has the mass that we measure from the experiments?
Wait, so I answered the question hopefully about the fermion couplings. The S coupling to Higgs can give us answers to why Higgs has the mass.
Yeah, it says the S coupling.
So can the singlet help with the Higgs mass, I think is the question. So in particular scenarios it can, right? So that's the NMSSM story that I told you about. So that's a supersymmetric story where basically you've added this singlet. So there is the other contributions to that, the MZ, which is the other, the tree level contribution from the doublets, etc. But you have the additional contribution from the singlet, right? So this was the superpotential for the Higgses. So you have the singlet coupling to the Higgses as well as the self-interaction. And when you actually compute out what the Higgs mass is, you get this MZ contribution as well as this lambda contribution from the singlet. So it can definitely help. Depends on the story. Yeah.
Okay, the second question is, could you explain again the role of a pseudoscalar field in the two Higgs doublet models?
So these are, this is a complex doublet, right? So what that means is that the neutral component, so doublet, that was in yesterday's talk. So a doublet is something which has two components. You have a charged component, and then you have a neutral component. So that's what these two Higgs doublets are, right? So you have two of these doublets. So now one of them we want to be the H125 one. But now you have this additional one. So you'll have the charged Higgs, okay? And then the second component will be neutral, but it's a complex neutral scalar. Now complex means that it has two parts, which is H plus IA. So I think I briefly talked about the CP violation. I mean, I know I did not do it justice, but I wanted to at least just mention it. But where did it go? No, not this. This. So your complex scalar, neutral scalar is given by H plus IA, right? And has 2 degrees of freedom. And so you have to treat them as, 2 particles that are there, one which has even CP even properties and one which has CP odd properties. So, and that's why it governs the couplings and decays and stuff like that.
Well, actually, I got the 2 more questions there. Okay, let's say, make them the last 2 questions. Okay, first one is, are there any massless fermions, or they are all massive?
They're all massive. I mean, we had hoped that at some point we had thought neutrinos could be, but we know that they have mass.
Okay, the last one. And thank you for your lecture and answers. And my last question, Tom again. And you said stop should be at the TeV scale. But if we, for example, upgrade the LHC and find no sign of stop, so we can only do more fine tuning for MSSM, but can't exclude this model.
Right, that's pretty much it, right? I mean, because in the simplest story, with just the MSSM is where we need the stops to be at the TeV scale, right? But as you saw in just the NMSSM story, right? Just adding one additional piece, right? And again, you should think the MSSM is the simplest thing, is the simplest SUSIE model that we could write down. I look at the standard model and it's completely non-minimal, right? The structure of it, right? So realistically, I don't think that the next step up is going to be the simplest model that we can think of, okay? And even on that, you add, so the MSSM, you add this one singlet and it completely changes the picture, right? Regarding the Higgs mass, etc. So, I mean, I don't know. I mean, so I don't think that you can exclude these type of models just yet. I mean, you can exclude, oh, I don't have a stop at 800 GeV, right? With all of the different parameters also defined, because it matters, like what's the other spectrum, what does the stop decay into, what are the other the neutralinos, etc., blah blah blah. That all plays a role in what you see. So you have to take all of these limits with that pinch of salt.
Okay, all right, that's all. Yeah, thank you very much, Nassim, for wonderful lecture. Yeah, thank you very much. All right.
Thank you.
Okay, thank you. Let's move on to the next lecture. Francesca, are you there?
Yes, I'm here.
Okay. Oh, great. So, okay, so next lecture is on the dark matter 2, and by Professor Francesca Ciaudaday, Durham University. And okay, so the topic is action dark matter. And okay, please share the screen. Yeah, looks okay.
Can you see my screen share?
Yeah. Then
okay,
can you make
great.
it? Oh yeah.
Yeah.
Yeah, full screen.
Okay, cool.
Okay. Thank you very much. Okay, the Francesca. Yeah, take it away.
Yeah, thank you. Yeah, thanks to the organizers for inviting me to give a talk here. It's really nice to be with you all, at least virtually. So today I'm going to talk about ultralight dark matter, and in particular axions. Axions are one very popular kind of ultralight dark matter, but I've included the ultralight dark matter in general in the talk because some of what I'm going to say would apply to any ultralight dark matter candidate. So I'm going to start off by just giving a quick introduction to ultralight dark matter and, why this is something we should be thinking about. Then I'm going to talk a bit about how we can describe ultralight dark matter using a classical field description, as opposed to the particle description that we might think of when we first hear about dark matter. Then I'm going to talk about how ultralight dark
Francesca,
matter.
are you? Sorry for disturbing you. And are you talking about the your slide that we are looking at? Oh, actually, we see the first slide still.
Oh, it hasn't. Oh, yeah. Sorry. Thanks for pointing this out. It says sharing is paused. Bring your shared window to the front. I wonder if I can do that. Okay, I'm just going to try stopping and starting again.
Yeah,
sorry, I'm very bad with all of Zoom.
It's okay.
Even now. Okay, so you can see it now.
Yeah. I think the second. Yeah, the second.
And if I go backwards and forward, you can still see.
Oh
it.
yeah. It's okay now. Yeah.
Okay,
all right,
great.
Thanks.
So I was just talking through this outline. So yeah, hopefully that was still clear. So then I'm going to go on to talk about axions, which are one very popular candidate for ultralight dark matter. And then I'm going to talk a bit about how we might detect axions using various different experiments and astrophysical techniques. So why should we be thinking about ultralight dark matter? So we have this basic problem that we know that there's this dark matter where we can see its gravitational effects on other matter, but we can't detect it in any other way. We only detect it gravitationally. And so this means we really have very little idea what it could be. You know, if it's an extra particle, we don't know what kind of particle it could be, or there's even some theories such as dark matter being mini black holes, where it wouldn't even be just a single extra particle or field. And we have so little knowledge about what dark matter is that we don't even know what its mass is, from, you know, all the way down to these like very, very light, you know, 10 to the minus 12 electron volt masses, up to 30 solar masses if we think dark matter is small black holes. So we need to look in this huge range of masses. I'm going to be thinking about this region, the sub-keV mass range, which is where we think about ultralight dark matter as living. And we know that there are a whole range of experimental search strategies that are relevant for this region, both experiments and astrophysical detection. The motivation for ultralight dark matter in particular often comes from the axion, which I'll talk more about later. The axion is a particular kind of ultralight dark matter, which is well motivated by both the strong CP problem and string theory, as I'll discuss later. More generally, we want to be exploring the whole dark matter parameter space at every mass where we think the dark matter might live. And ultralight dark matter has also been suggested as a solution to some small-scale structure problems, where it seems that in some cases having ultralight dark matter might fit our observations of dark matter structures better than heavier dark matter. But as we'll see, this is quite a complex area, and it's not clear whether that statement is true or not. One thing we know about ultralight dark matter is that to be the dark matter, it must be non-thermally produced. If ultralight dark matter started off in thermal equilibrium with the standard model and was produced that way, it would be moving at relativistic or near relativistic speeds. So this means it wouldn't be able to form the structures we see around us. We know dark matter must be non-relativistic, and for ultralight dark matter, this means we need a non-thermal production mechanism. So there's a number of ways we could do this. We could have it via the decay of a parent particle, via the decay of topological defects, or via the misalignment mechanism, which is kind of particular to dark matter that can be described by a scalar field, such as axions. So how does the misalignment mechanism work? It happens when we have a field that is created as a pseudo-Goldstone boson of some broken symmetry. So say we have that symmetry is spontaneously broken, and then that will create a massless axion field. Because this field is massless, it follows a random walk in field space. It has no potential. The amplitude of the field can be as big as you like. Then at some later point, non-perturbative effects generate a mass for the axion. And this means that the axion field is now at some kind of value that's displaced from the minimum of its potential. So we've created an energy density in that field via these non-perturbative effects that generate the axion mass. And what we then find is that the equation of motion for this field that has been displaced from its minimum looks like this. So here, phi is the axion field, m is its mass, and h is the Hubble constant. So we can see that this is the equation of a damped harmonic oscillator. It's oscillating with a frequency set by its mass, and the oscillations are actually damped by the expansion of the universe via this Hubble parameter. Now, when you work out what's going to happen to the energy density as this field undergoes damped oscillations, you find that the energy density actually redshifts like dark matter. So we've created this dark matter-like object via a production mechanism as the mass of the axion was generated. And we can also think of this field either as a classical field or as a large number of very, very cold axions. So even though the axions are really light, when they're produced in this way, they're very cold. There can be a kind of extra wrinkle to this story, because if we have this process happening in different patches of the universe, the axion field could take different initial values in those patches. And then we end up with a lot of kind of topological defects, axion mini clusters, and the evolution of the axion field becomes a lot more complex. But we still end up with something that is a lot of very cold axions that redshift like dark matter. So this has the right properties to be dark matter. Now, it may seem a little odd that these very light particles can be dark matter. The way I think about it is that we think everything's described by quantum field theory, and quantum field theory has two different classical limits. One is particles, so things that behave like ping pong balls, such as we think of WIMP dark matter, and the other is a classical field. And ultralight dark matter behaves as a classical field. What this really means is that it's a quantum field in a coherent state that can be described like this. So we have some operator that's giving us the field expectation value. And then when you take the expectation value of that, you get something that is behaving like this classical field. Another way of saying that is simply that each state has a very large occupancy. So there's a large number of axions in each state that the quantum field can be in. This means that this classical field description can, of course, only apply to bosonic dark matter. And indeed, all of the ultralight dark matter candidates are bosons. With fermions, the Pauli exclusion principle would prevent large occupancy of these states. And so you wouldn't be able to have something that behaved in this classical field way. We can write this classical field description typically in terms of an amplitude and a phase that evolves in time. And we can then further kind of redefine things. So we have this psi that we make up of from this amplitude and phase. And then when we do the maths of how this field behaves under gravity, we find that this psi obeys a Schrödinger-like equation. So it's like a time-dependent Schrödinger equation of this field moving under its own gravity. So the potential is this gravitational potential in the Schrödinger equation. And these equations really define how ultralight dark matter forms structures under its own gravity. Now note that for cold dark matter, so heavier dark matter particles that don't have this classical description, we can't use this framework. If we try to do this, we would find that A and alpha are not well defined. So starting from this equation, we're saying that ultralight dark matter is well approximated by a classical field limit of a quantum field theory, meaning that because we have large occupation numbers in each state, the fractional uncertainty in the amplitude and phase dispersion is small. However, as we'll see, this psi isn't a wave function in a physical sense. The fact that this looks like a Schrödinger equation is very useful because there's a lot of established methods for solving Schrödinger equations. But for example, this psi isn't normalized to 1, so we can't think of it as a wave function. What we find is that we can write this psi in terms of the square root of the number density of the ultralight dark matter particles. So it's really normalized to the dark matter number density rather than to 1. And this phase factor, which corresponds to the velocity of the dark matter. And these are really the two kind of key things we think of when we think of particle dark matter. So you can move between this field and this particle description. When we do that, we can write down some equations for the number density of dark matter in terms of what we can think of as a current term for this psi. So we have this equation, which is expressing kind of conservation of dark matter particle number. We also have this equation, which looks quite a lot like a fluid equation, with this extra term Q, which looks just kind of complicated, but we're going to discuss what it means physically. The fact that we have this Q term here means that dark matter doesn't behave like a perfect fluid. Q is often called the quantum pressure, and it can be thought of as a repulsive term that counteracts the gravitational potential. Gravitational potential is this phi. And we can understand this as arising from the 0-point motion of the ultralight particles that are making up dark matter. These very light particles are, of course, quantum particles, which means that they must obey the uncertainty principle. So they can't have a definite position and zero momentum, which would be a definite momentum at the same time. They have to have some 0-point motion when they're moving around. And it's this 0-point motion that we can think of as counteracting the gravitational potential that would tend to make them all just be still and in one place. This leads us to see that ultralight dark matter possesses a natural scale. And this is called the gene scale, and it's equal to the de Broglie length, the de Broglie wavelength of the ground state of that dark matter. So there's some length scale corresponding to the wavelength of our dark matter particles. And stability below the gene scale is then guaranteed by the uncertainty principle. So we're not going to get dark matter collapsing under its own gravity to sizes that are smaller than the gene scale. A kind of way of thinking about this in terms of Fourier transforms and power spectra is that power on scales below the gene scale is suppressed. And this is really the key fact that makes ultralight dark matter structure different from WIMP dark matter structure, that below the gene scale, you don't see structure anymore because everything is washed out by the 0-point motion of these ultralight particles. Okay, so how might this manifest observationally? So one thing we can do is look at the cosmic microwave background. The cosmic microwave background, of course, tells us about dark matter structures. And we find that if we have ultralight dark matter, the CMB would look different, that we would see a lack of structure on scales below the gene scale. And this actually puts quite stringent constraints on a large part of the ultralight dark matter parameter space. So here, these kind of red bits are the allowed region in different models. We've got log to the base 10 of the dark matter mass in electron volts on the x-axis. And on the y-axis, we've got the fraction of the total dark matter that this ultralight dark matter is making up. So below about 10 to the minus 26 electron volts, we can only have ultralight dark matter making up kind of 0.1 or so of the total dark matter density in the universe. For lower masses than this kind of 10 to the minus 30, the axion actually wouldn't be dark matter. If this were an axion, it would be dark energy. And this is going back to that harmonic oscillator picture. We would actually have something that was overdamped. So you wouldn't get oscillations, you'd just get a constant energy density. So these very low masses can't be dark matter at all. These higher masses are then, you can see, completely allowed by the CMB. So if the mass is greater than about 10 to the minus 25 electron volts, the CMB wouldn't really look much different between dark matter and cold dark matter and ultralight dark matter. So this is one thing we can do. I can see something in the comments. I'll leave questions until the end, I guess. So there are other ways we can search for ultralight dark matter, though. And one is by looking at the Lyman alpha forest. This is because light from distant galaxies and quasars is absorbed by intergalactic gas clouds. So these are just clouds of kind of mainly hydrogen gas that we can see throughout space, and they will absorb light. And in particular, there's an absorption line called the Lyman alpha absorption line, which is from the ground state to the first excited state of neutral hydrogen. And this absorption line is going to be redshifted depending on where that cloud is relative to us. And from the gas distribution of these clouds, we can infer the dark matter distribution. So we can perhaps see this a bit better with this little cartoon. So you've got some star or something over here that's emitting light. As that light travels to us, it's passing through various gas clouds. And each cloud is absorbing light at the same wavelength. So you're getting these absorption lines. But because these clouds are different distances from us, the lines are redshifted as they come to us. So each cloud, we actually get an absorption line at a different energy. And because we know the energy of the Lyman alpha line is measured on Earth, we can actually use this to infer the redshift of all of these clouds. And then we need to make the assumption that the gas distribution here is kind of following the dark matter distribution. And this is reasonable because we think the dark matter would attract these baryonic matter clouds gravitationally. So using this, we can kind of build up a map of where we think all of the dark matter is in the universe. And we find it forms this web-like structure called the cosmic web. And we can see the scales on which there's still a structure here. So by seeing which scales has structure in dark matter, we can rule out ultralight dark matter where that structure would be suppressed by the quantum motion of the ultralight dark matter. So we can use this to actually say that the mass of ultralight dark matter needs to be greater than about 10 to the minus 20 electron volts. So this is kind of imposing a stronger constraint than the CMB constraint. So I've told you about some constraints on dark matter, but why do we think that ultralight dark matter might still be a good candidate? One reason people were excited about ultralight dark matter is something called the cuspy halo problem. So this graph shows two different dark matter distributions for a galaxy. On the x-axis, I have the log of the distance from the center of the galaxy, which is the center, and this is the outskirts. And on the y-axis, I have the dark matter density. When we do simulations of cold dark matter, so not ultralight dark matter, we get this blue line, which is called a cusp. So the dark matter in our simulations, the density just keeps increasing towards the center of the galaxy. But when we do observations of how stars and gas in the galaxy is moving and use this to try to infer the dark matter distribution, we get something more like the yellow line. So it's kind of like a core. And this can be explained, this discrepancy between the simulation and the observations, if we have ultralight dark matter. Because ultralight dark matter, remember, gives us a suppression of structure below its de Broglie wavelength. And this is exactly what we're seeing here. Below some scale, the structure is just completely flat. And this is because in this region, the 0-point quantum motion of the dark matter particles would be preventing this kind of collapse into a very dense central part. However, others have argued that actually this difference between theory and observation could be explained even with heavy dark matter just by properly taking into account the effects of all of the stars and the supernovae in the galaxy. So this is again kind of an open question. So if we're interested in looking at ultralight dark matter, what kind of candidates can we have? So I've said it has to be a boson because we need to be able to have a very large occupancy of different quantum states. So that means it could be a vector particle, so a dark photon. It could be a scalar particle. Scalar particles tend to be quite constrained because they can mediate new forces very easily. So in particular, they're constrained by tests of the universality of gravity. It could also be a pseudo-scalar particle. So this is something with spin 0, like a scalar, but unlike a scalar, it's CP odd. So when you do a parity transformation, you get a minus sign. And the axion is in this category of pseudoscalars. So let's talk a little bit about what axions are, why we think they might exist. So you may have heard of the strong CP problem. Stop. You may have heard of the strong CP problem, which is telling us that there's a CP violating term here that's actually allowed in the QCD Lagrangian. So in this term, theta is a constant. This g squared over 32 pi squared is just some more constants. G is the gluon field strength tensor, and G tilde is its dual. So this is a term just involving the gluons that actually violates charge parity symmetry, which is when we do a mirror image of space and also exchange particles and antiparticles. Now, this is quite kind of theoretical and abstract, but the important thing about this term is it would lead to a neutron electric dipole moment. It would cause the neutron to have an electric dipole moment. Now, we've gone out and we've tried to measure the neutron electric dipole moment, and all of the measurements have said that it's 0. So this means that this theta term must be very, very small. And it's actually kind of even more puzzling than that, because the quarks, of course, also transform under the weak interaction. And this means that the effective theta term would actually be transformed by the weak interaction by adding argdet m, where m is the quark mass matrix. So the key thing to take away here is that you'd have these two different parameters coming from different parts of the standard model that would have to almost cancel each other out, or exactly cancel each other out, to 10 to the minus 9 to reproduce observations. And, you know, maybe the standard model is like that. Maybe it's just got this like weird quirk where these numbers cancel, but it seems a bit odd. So we would need these very fine-tuned cancellations to explain observations. I've just flagged this paper here, which some of you may be interested in. So this group recently actually did the calculation of the neutron electric dipole moment, the CP term, a different way. And they say that actually you wouldn't get any contribution from this argdet m. In fact, the weak and the strong CP terms together would actually lead to no neutron electric dipole moment. Calculation's quite subtle, and the argument is basically about the order in which some limits are taken. I haven't gone through the paper in enough detail to form an opinion, and I would say most physicists still think that the strong CP problem is a problem. I just thought I'd put this in just to show that, you know, these calculations are quite subtle, and this is really an ongoing area of research. But assuming the strong CP problem is really a problem, how do we solve it? One attempt at a solution can come from the Vafa-Witten theorem. So this theorem says that in parity conserving vector-like theories, such as QCD, parity conservation is not spontaneously broken. So another way of saying this is that in theories such as QCD, dynamical parity violating terms have zero vacuum expectation value. Now, this theta term would also break parity as well as CP. Now, of course, I can just write down a parity violating term. That's fine. That doesn't go against the Vafa-Witten theorem, because it's only dynamical parity violating terms that have zero VEV. So this theorem is from a paper by Vafa and Witten in 1984, which is a really nice paper. If you're interested, I encourage you to have a look. The derivation's very short, which is always pleasing, and is actually kind of deceptively simple. So it's quite a nice paper. So how can we use the Vafa-Witten theorem to solve the strong CP problem? The basic idea is that we promote theta to a dynamical variable so that the Vafa-Witten theorem will apply. To do this, we can't kind of get rid of the theta term entirely. All we do is we add on a new term, the axion A, which is dynamical, that couples to gluons in exactly the same way as the theta term. When we do this, the Vafa-Witten theorem guarantees that the total theta term will be zero in the ground state. Put another way, a potential is generated for this axion such that the total coefficient of GG tilde is zero. And this means there's no CP violation in this QCD sector. So how do we do this? Well, the theta term, it turns out, arises from an anomalous symmetry in QCD. So to make it dynamical, we have to introduce an additional global chiral symmetry for the standard model. This is called the Pesci-Quinn symmetry, which is spontaneously broken. Now, you might remember when you spontaneously break a symmetry, you get a Goldstone boson, which would be massless. Now, in our case, there's a little extra step in that the QCD chiral anomaly causes a non-perturbative explicit breaking of the Pesci-Quinn symmetry. So it's been both spontaneously broken and explicitly broken. And this means that the axion isn't completely massless as the Goldstone boson. It's got some small mass, which is given by this potential here. but it does retain a discrete shift symmetry. If the axion was like a pure Goldstone boson, then it wouldn't have any potential and it would have a continuous shift symmetry. So this is a bit more detail about that misalignment production mechanism I told you before. We have this spontaneous symmetry breaking followed by this explicit symmetry breaking, which gives the axion a mass. So that's the QCD axion, but we can also think about what are called axion-like particles, or ALPs. So these don't necessarily have anything to do with QCD. They are just ultralight pseudoscalar particles that exist in many extensions of the standard model. And they're pseudo-Nambu-Goldstone bosons of global U1 symmetries. So again, they're pseudo-Nambu-Goldstone bosons because there is both a spontaneous breaking of the symmetry and also an explicit breaking. So the symmetry was only approximate to start with. So where do these axion-like particles come from? The most popular source is string theory. So string theory is probably the most popular theory for quantum gravity. And in string theory, we find that we need to describe the universe in like 11 dimensions, whereas we only see 4. So we have to fold some of these dimensions up. And this is called compactification. And this process is what gives rise to ALPs at a large range of masses. And actually, these authors, Halvorsen et al., have worked out that string ALPs in many cases can have measurable effective couplings to electromagnetism, which is very exciting. I'll talk a bit more about that very soon. And these ALPs can also act as both dark matter and dark energy, following that ultralight dark matter classical field prescription that I described earlier. So if we want to detect these ALPs or axions, we need to know how they interact with the standard model. What we can do is use an effective field theory type approach and simply write down all of the interactions that are kind of allowed by the symmetries. And then we end up with something like this. So the axions have a kinetic term, they have a mass term, they have this coupling to gluons. They also have a coupling to electromagnetism. So F is the electromagnetic field strength tensor and F tilde is its dual. And you find that FF tilde is equal to E dot B, where E are the electric and magnetic fields. And then they will also have a coupling like this to fermions. These couplings G have a dimension of 1 over some mass scale. So typically this would be the mass scale at which the U1 symmetry is broken. For the QCD axion, mixing with the pion gives you a relationship between this FA and the mass of the axion. Whereas for a string ALP, MA and FA are free parameters. So what I'm going to do is really just think about this Lagrangian where the mass could be anything, these couplings could be anything, and just explore the whole parameter space. And then this will apply to both the QCD axion and to axion-like particles. So given this Lagrangian, which describes how the axion couples to the standard model, how might we go about looking for axions? How might we detect axion dark matter? Well, one thing is that we know the axion has this coupling to photons. So if we've got axion dark matter everywhere in space, we would expect that it would have some decay to 2 photons. If we calculate the decay width, we find something like this. And it's going to decay to photons whose energy is equal to the axion mass divided by 2. So we would expect actually a kind of photon line that we could see everywhere in space with an energy of half the axion mass. So this sounds great, but if you go and calculate this decay rate, it's like super tiny. Like you would definitely not be able to see it just going on this rate. You find that the axion lifetime is like longer than the age of the universe. yeah, it's 10 to the 32 years, so that wouldn't be very helpful. However, the decay rate of axion dark matter could be significantly enhanced by stimulated decay from ambient photons. So this works a bit like a laser, where if you had some photon whose energy was half the axion mass, it could interact with an axion and cause a stimulated decay of that axion into 2 more photons. And each of these photons could then go on to cause stimulated decays of other nearby axions. So this is exactly like how a laser works, and you could end up with this lasing of axion dark matter. And then this would have a much higher expected photon flux. And remember, the photons would all be at an energy of half the axion mass. So this means that they'd be kind of a bit easier to search for because they're all at the same energy. It's quite a clear signature. So people have explored what this would look like with the kind of next generation radio telescopes if you went searching for this axion line. And these authors have found that actually, you might be able, if you're lucky, to start searching for axion dark matter using this technique. Okay, so where else might we be able to find axions? Well, one thing is if axions exist, actually, even if they're not the dark matter, they just exist, you would probably produce them in stars. These are the Feynman diagrams for their production. So you can have axion production based on the axion's interaction with photons, or based on the axion's interaction with electrons. So if axions were produced in stars, how would that help us? Well, the axions would then provide an additional way for the star to cool. The axions would carry energy away from the star, and the star would cool down. So we can actually place bounds on how strongly axions can couple to photons and electrons by looking at the stellar cooling process, looking at stellar evolution. So you can look at, this is just a bit of detail about the different kinds of stars that lead to different bounds. And we can actually place a constraint on the axion photon coupling and on the axion electron coupling using this method. There have also been some authors that claim that actually there's some hints from looking at stellar cooling that axions do exist. You know, there's some anomalies in how stars seem to be cooling that suggest that maybe there is this extra cooling from axions. But a big caveat here is, of course, that stars are very complicated objects. So, you know, who can say? Maybe we've just got the modeling a bit wrong. The next one I want to talk about to search for axions is superradiance. So superradiance is actually a word that is used a lot in physics to mean several different things. What I'm talking about here is black hole superradiance. So you might know that if you have a Kerr black hole, so that's a black hole that's rotating, then the black hole will have some ergo region. In the ergo region, if a photon passes through the ergo region, or indeed any other particle passes through the ergo region, then it can actually gain energy from the rotation of the black hole, and it can actually escape from the black hole's orbit and leave with more energy than it started with. And this energy comes from the rotational energy of the black hole. So the black hole will slow down a little bit because of this process. So this is what we see on the left, that we can have some particle or radiation coming into the black hole and passes through the ergo region, and then an increased amplitude of radiation comes out. And then people said, well, okay, what if I surrounded my black hole by a mirror, and I could then have these particles being bounced back and forth through the ergo region, just kind of amplifying and amplifying in intensity each time. And yeah, that would happen. Of course, you can't actually go into space and surround a black hole with a mirror. But what you can do is think about a particle with a mass. So unlike a photon, something like an axion would have a small mass. And this means that it would become gravitationally bound to live near the black hole. So this gravitational attraction between the axion and the black hole replaces the mirror, and actually means that with a Kerr black hole, you would see the axion increasing and increasing in intensity. You'd get a larger and larger number of axions building up around the black hole, taking their energy from the rotational kinetic energy of the black hole. Now, of course, you need an initial kind of seed axion for this process, but this could actually just come from a quantum fluctuation. So if axions exist and you have these spinning black holes, you would see these axions build up and build up around the black holes. And as that happened, the black hole would spin down. So its rotational energy would decrease because it was all going into the axion field. So yeah, it's just what I said, axions build up around a Kerr black hole. What would you see? You could see a kind of Bose-Nova, it's called, explosion as the axion cloud collapses at some point. And you would see depletion of the black hole spin. So this means we can use black hole spin measurements to exclude regions of the axion parameter space where axion superradiance would have prevented black holes from reaching that spin. And we will get even better searches for axions when we can measure black hole spins using gravitational waves with advanced LIGO. Okay, so I know this has been a bit of a whistle-stop tour. We're going to review some of the constraints and ways of searching for axions at the end. The final way of searching for axion dark matter that I wanted to discuss in detail is axion photon conversion. So there's quite a lot of maths on this slide, but what this is basically saying is that the axion photon interaction means that in the presence of a background magnetic field, axions and photons can interconvert. So you could get a photon that was traveling along and would just turn into an axion. And this is what this equation is describing. We package the axions and the axion and the photon polarizations together into this axion photon vector. And then we see that because this matrix has off-diagonal terms, the axions and the photons can interconvert. So this effect is very exciting. Yeah, this is quite a striking effect. If you think you might have an axion which suddenly turns into a photon that we can see, or photons suddenly disappearing into axions. And this effect of axion photon conversion is probably the most widely used effect for searching for axions. There are loads of ways of doing this, but one of the most powerful is to look at galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe. They are groups of hundreds of galaxies, which is what we see here. They are obviously in large dark matter halos, and they also contain a warm X-ray emitting gas that suffuses the entire galaxy cluster. And this gas hosts a magnetic field, which provides the perfect conditions for axions and photons to turn into each other. So what I've circled here is the AGN at the center of a galaxy cluster. Now, if we look at this AGN using an X-ray telescope, such as the Chandra X-ray telescope, we will of course see the photons from that AGN, stands for active galactic nucleus, which is basically emission from stuff falling into a black hole. But if axions exist, some of these photons will have turned into axions in the magnetic field of the galaxy cluster. And these axions are invisible to us, so it'll just look like photons disappearing. So we will have this kind of survival probability of the photon, which is imprinted on the observed spectrum of this AGN. Here it's called NGC 1275, which is basically a catalog number for the AGN. So let's look at this photon survival probability for a photon traveling through a galaxy cluster in a bit more detail. So we see that it's, as you might expect, always less than 1, because these photons, some of them are turning into axions. And we can also see that it's not just flat, we have these oscillations. And this kind of goes back to the equations that I showed you earlier. They actually cause these oscillations in the photon survival probability in energy space. And if axions exist, we would then see these oscillations imprinted on the observed spectrum. So on the left here, we have the spectrum of an AGN in a galaxy cluster. Now, this is actually a Seyfert 1 galaxy, of a source in a galaxy cluster. The red line is the model with astrophysics only, no axions. And then these points are the data. So we see that the data is a pretty good fit to the model. There's kind of no evidence of any axions other beyond the standard model physics, anything funny going on. And on the right is a simulation where I have added the effect of axions. So we see that axions cause these wiggles of the data above and below the line that we would expect from astrophysics only. So we can go searching for these kinds of wiggles. And so far we haven't really seen any wiggles. And that means we can place bounds on how big the axion photon coupling can be. If we did see wiggles like this, then this would be, of course, some evidence that axions do exist. And the reason I've shared this method with you last is that actually for low mass axions, this is the best constraint that we have. So this constraint, looking at very bright sources shining through the magnetic fields of galaxy clusters, and using the fact that if axions exist, some of these photons would have turned into axions that we can't see, allows us to place the best constraints on the axion photon coupling. And of course, I don't need to tell you, we haven't found any axions yet using this method. And this method actually works whether or not axions are the dark matter. We haven't used anything about the axion dark matter that might be in the galaxy cluster. It's just about the existence of the axion particle. These bands with the Chandra X-ray telescope, and actually future X-ray telescopes such as Athena, will allow us to search for even smaller axion photon couplings. Okay, so I've given you, a few ways of searching for axions, but there's actually loads more, which are described on this plot. So here on the x-axis, we have the axion mass, and on the y-axis, the axion photon coupling. All of these points are regions where that coupling and that mass are excluded by some experiment. The exception is this yellow line, which describes where the axion would be if it were the QCD axion, so the axion that couples to gluons. But an axion-like particle from string theory could live anywhere on this plot. So I have talked a bit about constraints from stellar cooling. So that's this line. The stuff above this line is excluded. The constraints I've just spoken about here from looking at sources in galaxy clusters aren't shown because they actually live at lower masses further to the left. This very substantial constraint, this range 10⁻⁶ electron volts, is from a dark matter haloscope. So that's a big experiment on Earth that's trying to detect axion dark matter. And it's doing that using a resonant cavity. So that means it's using the dark matter mass, the fact that the dark matter has a specific wavelength, to set up a resonance such that you'd get high probability conversion from dark matter axions to photons. But we can see that there's a huge amount of effort going on. So this is the one time in this talk I'm plugging my own work. But one thing that I wanted to flag is that, as I discussed further in this paper, this plot really assumes that there's only one axion or axion-like particle, whereas actually in string theory models, you could easily get hundreds of axion-like particles. And the kind of mixing between these different axions can lead to very interesting effects, which might significantly change some of these bounds. So, you know, as often is the case in theoretical physics, the situation is more complicated than can really be presented on a two-dimensional plot. Okay, so just to sum up, I've given you quite a kind of whistle-stop tour of ultralight and axion dark matter, which hopefully just gave you a flavour of all the exciting research directions that are going on in this field. The takeaways are really that ultralight dark matter could make up all or some of the dark matter density. And at small scales, ultralight dark matter behaves very differently to the kind of heavier cold dark matter that we might initially think of. So to a weakly interacting massive particle or WIMP dark matter, for example. Ultralight dark matter is well described by a classical field description. And the axion is a well-motivated candidate for ultralight dark matter, which there's a lot of promising research directions to detect. So thank you so much for listening. And now I would be happy to answer any questions.
All right, thank you very much, Francesca, for a wonderful lecture on action. Okay, okay, let me read. I got several questions. First one from Himal. Can you explain dark matter and dark energy in simple, understandable form?
Yes, well, I'll do my best. Okay. So we think that actually only about 5% of the energy of the universe is in the kind of matter that we're used to from our everyday experiences. So kind of electrons, protons, that kind of stuff, baryonic matter, we call it. Now, the rest is made up of dark matter and dark energy. 25% of the energy density of the universe is in dark matter. So this is matter that we know exists because we can see its gravitational effects on other matter, such as stars and galaxies, but we can't detect it in any other way. So we don't know what it is. Axions are one thing it could be, but it could also be a kind of a right-handed neutrino, or it could be a supersymmetric particle, or really a whole host of possibilities. Dark energy is even weirder. Dark energy makes up 70% of the energy of the universe. And it's really a description of the fact that the acceleration of the universe is increasing. The expansion of the universe is accelerating. And we don't really know why. So you can just write it in with a cosmological constant. You can just make it happen, but that to a lot of people is an unsatisfactory answer. A lot of people think there's maybe some extra field or other effect that's causing the expansion of the universe to accelerate. And that's what we call dark energy. Hopefully that was somewhat intelligible.
Okay, thank you. And next question from Rishikesh. A bit long. Okay, let me read. Wouldn't converse be true with extragalactic background light being converted by magnetic fields in these gases and galaxies and converting to actions, and then these actions converting back to light in Earth's magnetic field, and therefore the result in a significant decrease in attenuation of extragalactic background light in regions where there is a perceived higher dark matter density as it measured from the Lyman alpha forest data question.
Yeah, this is actually a very perceptive question. This is a great question. So the effect that, yeah, if I understand right, that I think you're getting at is that you could actually have light that converts to axions and then converts back into photons. So you can kind of dodge attenuation of light using this effect. And this is actually something that people study as a way of searching for axions, particularly looking at very high energy gamma rays, which actually should be attenuated by pair production in the universe. So this is something people study. In terms of the Lyman alpha, I think the Lyman alpha absorption effect is just much stronger than we would expect the conversion into axions to be. So axion photon interconversion wouldn't have as strong an effect on the Lyman alpha forest, but exactly this effect is something people study for very high energy photons where it would be the strongest, so for kind of TeV scale photons. So yeah, that's a great question.
Okay, so okay, next one is let's see. Okay, from Durga, do Caspi halo problem exist in low mass galaxy or in all galaxies?
Okay, I'm not 100% sure on this one. I have to admit, it's not kind of my area as much, but I think it's in all galaxies. But yeah, the extent to which it's a problem depends on which simulations you believe. So it's hard to give a kind of exact answer.
Okay. All right. Okay, let's move on to the next one. And what can we understand from self-interacting dark matter? What is the most accepted solution for Caspi halo problem? Oh, that's related.
Yeah. Okay. So self-interacting dark matter is kind of a whole other kind of dark matter paradigm that has actually also been proposed as a solution to the Caspi halo problem, where dark matter would have a significant interaction with itself. So a dark matter particle with another dark matter particle, and this would also affect dark matter structure. In terms of the most accepted solution for the Caspi halo problem, it depends who you ask, but I would say that at this point, it's just baryonic effects. So it's just the fact that the dark matter interacts gravitationally with baryons, with stars, and then the feedback from that star formation actually ends up meaning that there is less dark matter in the center of the galaxy. So I think it's the kind of boring no new physics one, unfortunately.
Okay, so two more questions. Okay, the Doug again. And is there any possibilities of production of dark matter during the formation of black hole?
So I don't think that would be a direct way of producing dark matter. So, in general, a black hole would be formed by kind of gravitational collapse of any matter, baryonic matter, dark matter. It doesn't really matter to the black hole. So yeah, in general, I don't think that would be a specific way to produce dark matter.
Okay. Oh, I got a new one too. Okay, next one is the can action act like a light mediator between the dark sector and the standard model?
Oh yeah, great question. So in general, yes. However, the caveat is that the axion is a pseudo-scalar, which means it will couple to terms that are CP odd. So for example, rather than coupling directly to the electron current, it couples to the electron spin current. So all of its couplings to matter would be to its spin rather than to the total amount of matter. So this means it wouldn't mediate a fifth force in the normal way that we think of it. It would look a bit different.
Okay, thank you. And then last, I think that this is the last one. How is dark matter distributed in the universe? Does it have any effects on functioning solar system being 25% dark matter?
Okay, cool. Yeah. So dark matter isn't uniformly distributed throughout the universe. It forms a kind of web-like structure, which we call the cosmic web. And the nodes of that web, regions of very high dark matter density, are galaxies and galaxy clusters. Having said that, the solar system isn't 25% dark matter. And that's because the solar system is a huge baryonic matter overdensity. So most of the matter in the solar system is the sun and the planets rather than dark matter. So it doesn't have a large effect on the solar system itself.
Okay. So that's all in chat window. Digesh, are you there? Oh, I think the Digesh is monitoring the. Oh, yeah. Did you get the any question? Google Sheet?
No. I've been keeping track of that. No.
Oh,
so
okay.
Not for the previous session either. So.
Oh, okay. Yeah. All right. Okay. So I think that's all there. Thank you very much, Francesca, for your wonderful talk. And yeah, we thank the Nassim and Francesca again. So, and that's the, okay, we're done with day 2. Okay, thank you very much, Francesca.
Thank
and
you.
Nassim. Thank you
Thanks
very
for
much.
listening.
Thank you.
Thank you. Bye.
Okay, so with
thanks, Nobuchika. Thank you.
Yeah.
Thanks,
Okay,
Digesh.
so yeah, see you, everybody. See you tomorrow.
I guess the committee we have to stick around or join in.
Okay.
Have a meeting again.
Here, this Zoom.
No, we can use the other Zoom, so we can end this session. And
okay, I can. Okay. All right. Thank you very much. Thank you very much, everybody, and see you tomorrow. Okay. Bye bye.
Thank you.